Welcome back to Zzzcience, where we explore the universe one yawn at a time. Tonight, we are going on a slow and soothing journey into one of the biggest questions there is. Where does space stop? At first, it sounds simple, maybe even a little silly. But the deeper you fall into it, the more it stretches your mind, like the universe itself. As always, I hope this video helps you drift off gently, or at least puts your worries into perspective by zooming out a few billion light years. Of course, there is a small risk that it might be too interesting and keep you awake. But if that happens, at least you will have learned something fascinating along the way, before we float into the stars together. I would love it if you gave this video a like, and maybe subscribed if you have not already. It really helps this sleepy little channel grow. I would also love to know where you are watching from and what time it is for you right now. Are you tuning in from a cozy bed in Stockholm at 11:30 p.m. or listening from a couch in Melbourne at 3 o'clock in the afternoon while pretending to work? Let me know in the comments. It is always such a joy to see the sleepy science community scattered gently across the globe. Now, settle in. Get comfortable. You do not need to remember any of this. You do not need to take notes or stay alert. Just let the words wash over you like the cosmic background radiation. And as we begin this gentle voyage into the vast unknown, remember, this video is for educational and relaxation purposes only. It is not intended as medical advice or as a substitute for professional treatment. Ready? Let us begin. What exactly is space? That silent black canvas we see when we look up at the stars. What is it really? For most of us, space is simply nothing. A void. A big empty place where stars float, planets orbit, and socks mysteriously vanish. But space is anything but empty. It is one of the most active, mysterious, and misunderstood parts of the universe. To begin with, let us go back to the basics. For centuries, people thought of space as a simple backdrop. Imagine a stage in a theater. Space was the flat wooden floor, and planets and stars were the actors moving around on top of it. This idea came largely from Sir Isaac Newton, who believed that space was absolute. A fixed, unchanging arena in which everything happened. Time ticked along at the same pace for everyone, and space was just the three-dimensional grid that held it all. Then along came a fellow with wild hair and a tendency to scribble on chalkboards. Albert Einstein shattered that tidy image and replaced it with something far more strange and elegant. According to Einstein, space is not a passive backdrop at all. It is a living, stretchy fabric, one that bends, twists, and warps in the presence of mass and energy. Together, space and time form a four-dimensional construct called space-time, and this dynamic stage actually responds to what is happening on it. To visualize this, picture a trampoline. Place a bowling ball in the center, and the fabric dips. Now roll a marble across the surface. Instead of going in a straight line, it curves around the dip. That is a bit like how gravity works in Einstein's universe. Massive objects like stars and planets bend the space-time around them, and that curvature is what we perceive as gravity. We do not fall toward Earth because it pulls us like a magnet. We fall because Earth has warped space-time and we are rolling into the dip. Now, you might be thinking, okay, fine, space bends. But when there is nothing in it, when we are in the gaps between stars, is that just nothing? Not quite. Even in the darkest, loneliest corners of the universe, space is still full of activity. Thanks to quantum mechanics, we now understand that empty space is not truly empty at all. At the smallest scales imaginable, far smaller than atoms, space is buzzing with what physicists call quantum fields. These fields are not things in space. They are space. Every particle in the universe arises from its corresponding field. An electron comes from the electron field, a photon from the electromagnetic field. And even when no particles are present, these fields are never completely still. They fluctuate constantly, producing tiny momentary particles that appear and vanish like cosmic fireflies. This jittery energy in empty space is called vacuum energy. It is a bit like the surface of a pond. From far away, it looks calm, but up close, you see ripples, disturbances, the occasional jumping fish. What seems smooth and featureless from a distance is actually full of hidden motion. This is why physicists say the vacuum is not empty. It seethes with potential. Particles pop in and out of existence in fleeting pairs. Virtual particles, as they are called. They cannot be observed directly, but their effects can be measured. For example, they influence how electrons behave around atomic nuclei and even contribute to the mysterious phenomenon we call dark energy, which is believed to be pushing the universe apart faster and faster. So no, space is not just the place where you lose your keys or send your thoughts during awkward conversations. It is alive with structure and movement, even when there is nothing visible to the eye. And it gets even stranger when you consider that space itself can expand. Not the things in it moving farther apart, but space itself stretching between them. That idea too comes from Einstein's theories and underpins our modern understanding of cosmology. But let us pause for a moment. It is easy to feel overwhelmed by the idea that the emptiest thing in existence is actually humming with energy and geometry and fields we cannot see. Yet in a way that makes it all the more comforting, because it means the universe is not just a cold void. Even in its quietest, darkest moments, there is still something happening. A soft background hum, like the quiet crackle of a fireplace or the rustle of leaves on a still night. And that hum, those fluctuations, that restless vacuum, is a reminder that space is not just the absence of matter. It is a physical entity with properties of its own. It can bend and stretch, expand and ripple. It has energy. It has temperature. In fact, even the vast emptiness between galaxies is thought to be just a few degrees above absolute zero, still faintly warmed by the leftover glow of the Big Bang. So, when we ask, what is space? We are not talking about an empty void. We are talking about a rich, structured fabric that connects every atom, every galaxy, every living being. Space is not where things happen. Space is one of the things that happens. It is part of the story, not just the stage. And maybe that is the strangest thing of all. The more we study space, the more it refuses to be empty. It twists, it hums, it fluctuates, it expands. Even when it seems to do nothing, it is never really doing nothing at all. And as for those missing socks, well, space might not be to blame. But if they did fall into a pocket of warped space-time, at least they would be part of a very exclusive scientific mystery. Imagine standing on a quiet hilltop under a clear night sky, gazing up at a universe that stretches in every direction. It feels endless, infinite, eternal. But what if I told you that there is a cosmic limit to what you can see? A kind of celestial bubble that surrounds us. Not because the universe ends there, but because light simply has not had time to reach us from beyond. This is not science fiction. This is the observable universe, and it is the part of the cosmos we can actually detect. Light, radiation, gravitational waves, anything that has managed to travel to us since the beginning of time. That word observable is key. It does not mean that everything outside of it does not exist. It just means we are not lucky enough to have seen it yet. Now here is where things get interesting. You might think logically that the farthest we could possibly see would be about 13.8 billion light years away. After all, that is how long the universe has been around, give or take a few 100 million years. And if light moves at, well, the speed of light, would that not be the edge of our vision? If only the universe were that straightforward. Because of the way space itself expands, that boundary is actually much farther out. What we call the observable universe has a current radius of about 46.5 billion light years in every direction, making it roughly 93 billion light years across. Yes, you heard that right. Even though the universe is only 13.8 billion years old, the distance to the farthest galaxies we can see is more than 3 times that, because space has been stretching the whole time. Think of it like this. Imagine placing raisins on a loaf of bread and popping it in the oven. As the bread rises, the raisins move farther apart. Now imagine a photon of light is emitted by one raisin toward another right as the baking begins. By the time the light arrives, the bread has expanded. The photon's journey was not across a static distance. It was across a growing one. The destination moved farther away as the light was en route. That is more or less what happens on the grander scale. This brings us to the concept of the cosmic horizon. It is not a wall. You are not going to fly a spaceship out there and suddenly bonk into the edge of the universe like a cosmic cartoon. Instead, it is more like a gentle fading of information. Beyond this horizon, light from distant regions has not had enough time to reach us since the Big Bang. It is as if we are standing in a vast fog, only able to see the nearby glow. The rest is shrouded, not because it is not there, but because the universe has not given us the signal yet. This horizon forms the boundary of our observable universe, and it is always changing. As time goes on, light from more distant regions will arrive, and the bubble will expand. At the same time, because of the accelerating expansion of space, some galaxies are moving away from us so quickly that the light they emit now will never ever reach us. Not even in trillions of years. They are receding faster than light itself. Not because they are breaking any cosmic speed limit, but because the space between us is stretching too fast. In a very real sense, the universe is slipping out of our grasp now. Let us take a gentle pause to appreciate something beautiful. Every single star, every galaxy, every smudge of light we see in the night sky is within our observable universe. That is the good news. The bad news, there is almost certainly far more beyond it, maybe infinitely more, that we will never see, touch, or study. We are surrounded by a vastness that mocks our instruments, and yet we can only peek through this little bubble of perception. What is even more humbling is that everyone, everywhere, has their own observable universe. If you were standing on a distant galaxy 10 billion light years away, your cosmic bubble would overlap ours a bit. But it would also include regions we will never know. In other words, the observable universe is not the universe. It is just our slice of it. And what a slice it is. Roughly 2 trillion galaxies, each containing millions to trillions of stars. That is a lot of starlight crammed into our little observational bubble. The photons from some of these galaxies have been traveling for billions of years only to be finally absorbed by the back of your retina or your telescope sensor. Tonight, some of that light began its journey before Earth had even formed. That ancient glow is a kind of time machine, a message in a bottle from an epoch long past. And yet, as rich as this observable universe is, it may represent only a tiny fraction of the total universe. Beyond the cosmic horizon, space might continue forever. It might be curved or flat, or even loop back on itself in some strange multi-dimensional geometry. But we will never know. Not with light, not with any signal bound by time and the speed of causality. There is a kind of peacefulness in that limit. Knowing we cannot see everything reminds us that our place in the cosmos is fundamentally local. We do not have to understand or control the whole universe to find meaning in it. Sometimes it is enough just to sit beneath the stars and know that you are part of something much larger than yourself. And while 93 billion light years sounds massive, and it is also just the visible frosting on an unfathomably big cosmic cake. What lies beyond? We can only guess. Maybe more galaxies, more structure, more dark matter and dark energy. Or maybe something stranger still. But for now, we are here, drifting inside a glowing bubble of light, information, and time. A bubble shaped not by borders, but by the patient journey of photons and the limits of cosmic time. It is not a prison. It is a gift. A slowly expanding gift that lets us see deeper into the story of the universe with every passing day. When we look up at the night sky, we often imagine that we are seeing the universe as it is right now. But that is not quite true. What we are really seeing is the universe as it was. Every star, every galaxy, every glowing dot in the sky is a time capsule. The farther away it is, the older the light we are seeing. In fact, looking across the universe is a bit like rummaging through a cosmic attic. Each layer of light takes us deeper into the past. Let us start with the humble light year. A light year is the distance that light travels in 1 year, about 6 trillion miles or nearly 10 trillion kilometers. When you look at a star that is 100 light years away, the light reaching your eyes left that star 100 years ago. You are seeing it not as it is, but as it was when your great-grandparents were still young. Now stretch that idea across the vast expanse of space. Some of the galaxies we observe are billions of light years away. That means the light we detect from them began its journey before our solar system even existed, long before Earth formed its oceans or developed its first microbial life. That light was already racing toward a future observer, toward you. This leads us to something astronomers call look-back time. It is a way of expressing how far into the past we are seeing when we observe distant objects. If a galaxy is 8 billion light years away, its look-back time is 8 billion years. That light has been traveling across space for more than half the age of the universe, arriving just in time to illuminate your evening stargazing or to land on the mirrors of a telescope, orbiting above Earth. In a strange way, space is full of ghosts, echoes of what once was. We are not seeing galaxies as they are today. We are seeing them frozen in earlier chapters of their existence. Some of them may not even exist anymore. They might have merged with other galaxies, changed shape, run out of star-forming gas, or simply drifted beyond the reach of light due to the expansion of space. What we see is a kind of cosmic fossil record written in photons, but it gets even more fascinating. As light travels through the expanding universe, it stretches. This phenomenon is known as redshift. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelength of light lengthens when its source moves away. Since space itself is expanding, nearly all distant galaxies are receding from us. and the light they emit becomes stretched into longer, redder wavelengths as it travels. Hence the name redshift. By measuring the amount of redshift in the light from a galaxy, astronomers can determine how far away it is and, more importantly, how long that light has been on its journey. A high redshift means a very distant galaxy and a very ancient glimpse into the early universe. This redshifted light holds clues about the structure, age, and history of the cosmos. It tells us how fast the universe is expanding, how galaxies evolve, and even hints at the mysterious forces like dark energy that are shaping everything on a grand scale. Every color-shifted photon is a little messenger from the past, carrying encoded stories of where it came from and what the universe was like back then now. Let us talk about telescopes, our cosmic time machines. When you look through a telescope, you are not just seeing things more clearly. You are seeing them more deeply into time. A backyard telescope might show you Jupiter's clouds from about 40 minutes ago. A more powerful observatory could show you a galaxy as it appeared 500 million years in the past, back when life on Earth was still experimenting with fins and gills. Then we have the heavyweights, the great observatories like Hubble, James Webb, and future successors waiting in the wings. These instruments can peer so far into space and thus so far back in time that they capture the faint light of the first galaxies to ever form. We are talking about structures that began taking shape just a few 100 million years after the Big Bang. Picture yourself standing in a field early in the morning. The grass is still wet with dew. The air is cool, and a soft fog rolls gently across the horizon. You can only see a short distance ahead, maybe a few trees, the outline of a distant hill. But beyond that, everything fades into a pale blur. You know the world continues past the fog, but your vision cannot reach it just yet. In a way, that is what it is like to live inside the universe. No matter how powerful our telescopes become, there is a limit to how far we can see. Not because of fog in the traditional sense, but because of time, distance, and the peculiar nature of the expanding cosmos. These limits are what we call cosmic horizons, and they define the boundaries of our observable universe. Now, unlike the tidy horizon on Earth, where sky meets land, cosmic horizons come in a few different flavors, each with its own rules and significance. The first is called the particle horizon. Think of it as the maximum distance from which light or any other signal could have reached us since the universe began. It marks the outermost edge of the observable universe, the ultimate limit of our current cosmic bubble. The particle horizon is shaped by time itself, since the universe has existed for about 13.8 billion years. And because space has been expanding during that time, the furthest distance light could have traveled to reach us today is around 46 billion light-years in any direction. That is why the observable universe is roughly 93 billion light-years across. It is the grand perimeter of everything we can currently detect. But do not mistake this horizon for a wall. There is no border, no glowing edge with a no entry sign. Instead, it is a limit woven into the very fabric of time. Like standing on the shore of a vast sea, you can look out as far as the light allows, but you will never see beyond that gentle curve. Not because there is nothing there, but because the signals have not had time to arrive. Next, we come to the event horizon of the universe, not to be confused with the dramatic kind surrounding black holes. In cosmology, the event horizon refers to the boundary beyond which events cannot ever affect us, no matter how long we wait. It is the cosmic line in the sand. Anything beyond this point is retreating from us faster than the speed of light due to the expansion of space. That light, no matter how persistent or patient, will never catch up to us. It is a little bit like trying to send a message to a friend on a raft floating away down a river. You throw a bottle with a note inside, but the current is so strong that the raft drifts faster than the bottle can reach it. No matter how hard you try, the message will never be delivered. That is the event horizon, where communication, even light itself, becomes impossible. At this very moment, the cosmic event horizon is thought to be around 16 billion light-years away. That means there are regions of the universe we can see now. But if those regions emit new light today, that light will never reach us. We are watching galaxies that are, in a very real sense, slipping away. Visible today, but destined to fade from view forever. Finally, we have the cosmological horizon, which is sometimes used interchangeably with the particle horizon, but can also refer to more general boundaries in space-time. It is a term that encompasses these observational limits and reminds us that horizons are not just visual, they are deeply tied to the physics of the universe itself. The cosmological horizon can be thought of as the moving edge of the observable universe, expanding outward as time goes on, and light from more distant objects has the chance to arrive. These horizons are constantly shifting and evolving. As the universe ages, the particle horizon grows. More light has time to reach us. But because of dark energy and the accelerated expansion of space, the event horizon shrinks in relevance. More galaxies move beyond our reach. The universe becomes a place of increasing isolation, not because it is empty, but because the light from its distant corners is falling behind. To put it another way, the universe is like a slowly inflating balloon. Dots on its surface drift apart, and the farther they are, the faster they move away. We can only see the dots close enough for their light to make the trip. Beyond that, the light stretches and dims until it vanishes into the expanding abyss. There is something haunting, but also peaceful about these limits. It is a quiet reminder that we are not omniscient observers. Our view is shaped by cosmic history, by how long light has been traveling, and by the strange properties of the space it travels through. We are peeking through a window that is enormous, yes, but still finite. Some regions of the universe will always remain a mystery, no matter how patient or clever we become. Not because we lack technology, but because of the very nature of space-time itself. These unseen realms are not behind a curtain waiting to be pulled back. They are beyond the reach of information, forever unknowable, and yet, even within these boundaries, we have managed to learn so much. We have mapped galaxies, measured background radiation, and traced the fingerprints of the Big Bang. We have used the fog of the particle horizon to understand the structure of the cosmos and the glow of ancient light to piece together its story. The horizons do not limit our imagination, they frame it. Like the rising sun burning off the morning mist. Every new discovery pushes the fog back just a little, revealing more of the landscape. But some parts will always remain hidden behind the curve, behind the stretching, swelling boundary where light will never arrive. Still, here we are, spinning quietly in a corner of the universe, watching photons arrive from billions of years ago, reading the messages they carry, and dreaming about what lies beyond the next soft bend in the cosmic road, even if we cannot see it all. Even if parts of the universe are forever beyond our reach, the beauty is in the trying, in listening to the quiet hum of light, in following it to the edges of knowledge, and in knowing that while we may never see the full view, we are part of the story just the same. Not too long ago, in the grand timeline of human curiosity, people believed the universe was pretty steady. Galaxies were out there, stars were shining, and everything more or less stayed put. A quiet, eternal cosmos. But in the early 20th century, a game-changing discovery quietly rose from a mountaintop observatory. And the universe has not sat still since it was Edwin Hubble. Yes, the same name we gave the famous space telescope, who first noticed something peculiar. While studying distant galaxies, he observed that their light was consistently. That meant the galaxies were moving away from us, and the farther away they were, the faster they seemed to recede. This was not a random trend or a cosmic coincidence. It was a pattern, a law. Space itself, it seemed, was expanding now. This is not quite the same as galaxies zooming through a fixed static space like cosmic race cars. It is not like they are bursting outward into a pre-existing void. What is actually happening is stranger and more elegant. Space itself is growing. Imagine that space is the thing stretching, and galaxies are being carried along with it like raisins embedded in a rising loaf of bread. That image, raisin bread, is a gentle and surprisingly accurate way to picture it. Think of the dough as space and the raisins as galaxies. As the dough bakes and rises, it stretches in every direction. Each raisin finds itself farther from the others, not because it is moving on its own, but because the dough between them is expanding. There is no central raisin, no preferred direction, just a uniformly growing loaf. This is how the universe works on a large scale. Galaxies are not rushing outward through space like cannonballs. They are being carried away from each other as the fabric of space itself stretches. That is why, no matter where you are in the universe, it looks like everything else is moving away from you. From every galaxy's point of view, space is expanding in all directions. It is a bit like being in a rising bubble. No matter which bubble you are in, all the other bubbles seem to be drifting away. The universe is not expanding into anything. It is just expanding. There is no outer shell, no edge it is racing toward. Instead, the distances between unbound objects simply grow over time, as if the cosmic measuring tape is slowly lengthening. This idea of an expanding universe was so radical when Hubble proposed it that even Albert Einstein had to revisit his own equations. Originally, Einstein had added something called the cosmological constant to his general theory of relativity to make the universe stand still. He thought the cosmos had to be static, and his equations, left to their own devices, suggested otherwise. When he heard about Hubble's findings, he famously called the addition of the constant his greatest blunder. Though, ironically, the concept has since made a comeback in explaining dark energy. The universe seems to have a sense of humor, too. But back to the expansion. One of the most beautiful consequences of Hubble's discovery is that it allowed us to rewind the cosmic clock. If galaxies are all moving away now, they must have been close together in the past, much closer. This led scientists to the idea of a hot, dense beginning to the universe. What we now call the Big Bang. The term Big Bang can be a little misleading. It was not an explosion in space, like fireworks going off in a dark field. It was more like the rapid swelling of space itself, everywhere, all at once. No center, no blast radius, just the entire universe suddenly stretching out of a state of extreme density and heat. You cannot point to a location in the sky and say, that is where the Big Bang happened, because it happened everywhere, including right where you are sitting. That expansion is still going on today, nearly 14 billion years later. Galaxies continue to drift apart, and the light they emit continues to stretch with them. The farther away something is, the more its light gets redshifted by the expanding universe. It is a cosmic stretching of time and space that shapes every observation we make. Interestingly, the universe's expansion does not affect everything equally. It works on the grand scale between galaxies and galaxy clusters, but it does not pull your morning coffee farther from your lips or separate the atoms in your chair. That is because gravity and other forces dominate on smaller scales, keeping things nicely glued together. The Milky Way is not expanding. Your neighborhood definitely is not expanding. And unless your washing machine is eating socks again, even your laundry pile is relatively stable. But on the cosmic level, the expansion continues. And what is more, it is accelerating. This discovery, made in the late 1990s, came as a surprise. Scientists had assumed that the expansion might be slowing down due to gravity. Instead, they found that some mysterious force, now called dark energy, is causing it to speed up. The dough is not just rising, it is rising faster and faster with every passing moment. No one is entirely sure what dark energy is. It might be an inherent property of space itself, or a field we have not yet understood. But whatever it is, it now dominates the energy budget of the universe. That gentle stretch is turning into a cosmic sprint, and galaxies are receding from one another at ever greater speeds. It is a little poetic in a quiet way. The universe began with everything close together, dense and unified. Over time, it expanded, cooled, formed stars and planets, and all the ingredients for life. And now it continues to drift outward. Stars aging, galaxies moving apart, space stretching into the unknown. Like a story that opens with a bang, blossoms into complexity, and drifts off into a gentle, infinite epilogue. There is no sound in space. But if there were, maybe it would be the soft creak of rising dough, the occasional pop of a bubble, the slow shift of warm expansion. Not a violent noise, not a shout, just the peaceful hum of a universe becoming itself. So when we say the universe is expanding, we are not talking about things flying away from some central point. We are talking about the very fabric of reality, stretching as calmly and steadily as a loaf of bread in the oven. It is one of the most profound discoveries in science, and also one of the most comforting. The idea that change can be slow, steady, and beautiful. And as we sit here surrounded by stars and bathed in ancient light, we are part of that expansion. Every breath, every heartbeat, every thought you have ever had has taken place on a little rock, spinning in the middle of rising cosmic dough. It is enough to make you hungry for answers, or at least for a midnight snack. In physics, there is a hard and fast rule that is never meant to be broken. Nothing can move faster than light. Not a spaceship, not a signal, not even your cousin Greg, who claims he once dodged traffic by running across 6 lanes in record time. According to Einstein's theory of relativity, the speed of light, about 299 million meters per second, is the universal speed limit, and nothing with mass can ever reach or exceed it. And yet, out there in the great cosmic distance, astronomers have observed something that seems to defy this rule. Galaxies that appear to be moving away from us faster than the speed of light. Entire clusters of stars and dust slipping beyond our grasp at superluminal speeds. It sounds like physics should be panicking. But do not worry, everything is fine. The universe is not breaking the rules. It is just playing a very clever game with them. To understand what is going on, we need to revisit a key idea. Galaxies are not flying through space like comets in a vacuum. Instead, space itself is expanding and galaxies are being carried along with it. Think of space as a rubber sheet with dots on it. If you stretch the sheet, the dots move farther apart, not because they are crawling across the surface, but because the surface itself is growing underneath them. This is how galaxies can appear to recede from each other faster than light. It is not that they are breaking the speed limit. It is that the space between them is stretching so quickly that the total separation increases at a rate greater than light can bridge. The galaxies themselves remain obedient little citizens of physics. It is space that is doing the legwork. Here is a helpful way to picture it. Imagine you are standing on a treadmill that is gradually speeding up. You try to walk towards someone at the other end, but the treadmill is moving backward faster than you can walk forward. Eventually, no matter how hard you try, the distance between you and the other person keeps increasing. It is not that you are walking too slowly. It is that the ground beneath you is working against your motion. In the case of the universe, light is trying to travel through expanding space. But in some regions, especially very far away, space is expanding so rapidly that the light never makes progress toward us. It is like trying to paddle a canoe upstream during a flash flood. The water flows too fast and your boat is swept farther away despite your best effort. This does not violate relativity because that theory only forbids objects moving through space faster than light. It does not say anything about how fast space itself is allowed to grow, and it turns out space has quite the flair for dramatic entrances. Take, for example, a period called cosmic inflation. This was a mind-bendingly brief moment just after the Big Bang when the universe expanded at an absolutely staggering rate, far faster than the speed of light. In less than a trillionth of a second, the universe grew from something smaller than a proton to something the size of a grapefruit, or possibly larger. Try explaining that expansion in a recipe. And again, this faster-than-light swelling did not break any rules. It was space doing the expanding, not particles racing through it. It is one of the few times in physics when faster-than-light travel is not only allowed, but encouraged. Just do not try it in a spaceship. Your engines will not appreciate the suggestion. This rapid inflation smoothed out the early universe, ironing away wrinkles and unevenness like a cosmic steam press. It also helps explain why the universe looks so uniform in every direction, despite the fact that distant regions have not had time to exchange information. Inflation spread everything out so quickly that local differences became subtle and stretched far apart. Even now, billions of years later, we are still seeing the effects of that expansion. Space continues to grow, carrying distant galaxies farther and farther away from us. Some of those galaxies are now receding faster than light, not because they are speeding up, but because the space between us is growing faster than light can close the gap. This means that there are regions of the universe we can never see. No matter how long we wait, their light will never reach us. And if they emitted new light today, that light would be swept away into the deepening void. These galaxies are not lost because they are moving too fast. They are lost because the road between us is stretching out faster than their signals can travel. It is a bit like trying to send a postcard across a river where the opposite shore is drifting away faster than you can throw. No matter how many stamps you stick on it, the postcard is never going to make it. Eventually, even the idea of delivery becomes meaningless. So when astronomers say some galaxies are receding faster than light, what they mean is this: due to the expansion of space, the separation between us and those galaxies is increasing at a rate faster than light can keep up with. There is no violation, no rebellious physics, just a clever interpretation of how space and time can flex in ways our instincts do not always understand. In fact, This cosmic trick has another strange consequence. There are galaxies we can see today, clear as day through our best telescopes, that have already crossed this horizon. They are still visible because the light they emitted long ago is still arriving. But their newer light, being produced now, is already out of reach. It will never get to us, not even if we wait an eternity. It is a little like watching the taillights of a car that has just turned a corner. You can still see the glow, but the car itself is already gone. Cruising down a road you will never follow. The light is a ghost, a message from a past that can no longer be updated. This reality has a certain peaceful melancholy to it. The universe is full of stories we will never hear, stars we will never see, galaxies we will never know existed. Not because we did not look hard enough, but because the cosmos itself is drawing the curtain, stretching the stage beyond our view. Yet this too is part of the wonder. The fact that we have been able to glimpse so much of the universe's past is nothing short of miraculous. Despite all the distance and distortion, we have still managed to see billions of light years in every direction. We have caught ancient photons in mid-flight, pieced together the origins of galaxies, and even traced the faint afterglow of the Big Bang itself. And all of this has happened from a tiny planet orbiting an unremarkable star in an average galaxy. In a universe where space moves faster than light, it is enough to make you feel small, but also strangely lucky. Because here we are, listening to the whispers of an expanding cosmos, watching light struggle to reach us, counting galaxies as they fade into the distance. And all the while, the dough of the universe continues to rise, carrying with it the dreams of curious beings who once wondered just how far light could go. When we think about the universe, it is tempting to picture it like a big black box, a vast rectangular space with a top and bottom, left and right, front and back, just floating in something. Asterisk, asterisk maybe. It has edges, asterisk, asterisk, maybe it goes on forever. Asterisk, asterisk, maybe. There is a giant cosmic wall with a do not enter sign and a very bored security guard. Asterisk, asterisk, but the real shape of space is much more subtle and much more fascinating. It turns out that space is not necessarily flat like a tabletop. It might be curved. In fact, it might be positively or negatively curved, or just ever so gently flat. And this is not just a matter of aesthetics. The geometry of the universe has deep implications for how it evolved, how it behaves, and whether it might one day curve back in on itself or continue stretching forever. Let us start with the three main possibilities. The first is a flat universe, like an infinite sheet of paper. In this model, the rules of geometry behave just as we learn them in school. Parallel lines never meet. Triangles always add up to 180 degrees, and if you travel in a straight line, you will never loop around. You will just keep going indefinitely through an endless cosmic plane. The second option is a closed universe, shaped like a sphere, or more precisely, the three-dimensional equivalent of a sphere. Here space curves back on itself. If you were to set off in a straight line in any direction and somehow avoided stars, planets, and all other space debris, you would eventually return to your starting point. Like walking in a straight line around the surface of the Earth, you would not fall off. You just keep going in circles. Though it might take several billion years and an industrial-strength pair of shoes. The third possibility is an open universe, shaped like a saddle. This space curves outward like a Pringle. In this geometry, parallel lines eventually diverge. Triangles add up to less than 180 degrees. And if you tried to go around the universe, you would never come back to where you started. You would simply drift farther and farther out into the cosmic vastness. These shapes, flat, closed, and open, are not just abstract ideas. They are tied directly to the universe's overall density and energy content. Specifically, how much matter and energy exist compared to what would be needed to make the universe perfectly balanced. This critical density determines whether space bends inward, outward, or not at all. If the actual density is greater than the critical density, space is closed and positively curved. If the density is less, it is open and negatively curved. And if the densities match just right, the universe is flat. It is a bit like the Goldilocks of cosmology. Not too much, not too little, but just enough to keep the geometry straight. And how do we measure this? As it turns out, the universe leaves behind clues in the cosmic microwave background, the ancient light that has been traveling since shortly after the Big Bang. By analyzing the tiny fluctuations in this faint glow, scientists can determine how space bends light over vast distances. It is like using the pattern of ripples on a pond to understand the shape of the shore. So far, the evidence suggests something remarkable. Our universe appears to be very, very close to flat. Not perfectly flat perhaps, but close enough that any curvature is too small to detect with current instruments. It is like standing on a massive plane that might have a slight bend somewhere over the horizon, but as far as you can see, it is pretty straight. Now, here is where things get really interesting. A flat universe can still be infinite or not, and a closed universe, surprisingly, can be finite but unbounded. That phrase sounds like a contradiction at first, like saying you have a mug that is full but holds no coffee. But it makes sense with a little thought. Take the surface of a sphere. It is finite. You can measure the total area, but it has no edges. You can walk around the surface of a globe forever and never fall off the edge because there is no edge. The whole surface connects back on itself. Now, take that concept and apply it to a three-dimensional version. That is what cosmologists mean by a space that is finite but unbounded. It is a closed loop, a self-contained bubble of geometry. This kind of space does not have a border. There is no place where the universe ends and something else begins. It is just space curving back around in a grand, subtle loop. And because we live within it, we would never be able to tell directly. We just keep drifting forward, thinking we are going straight, while quietly bending back toward home. Even in a flat or open universe, infinity brings its own peculiar flavor. An infinite universe means an endless number of galaxies, stars, and potentially even repeating patterns. Somewhere out there, if the universe is truly infinite, there could be another version of you listening to this same video, possibly in a slightly different pair of pajamas. Now, it is worth noting that we can only observe a small fraction of the universe. Beyond our observable horizon, we do not know how space behaves. It could be flat forever, or it could curl into a loop we are too small to detect. The curvature might be so slight that even a light beam traveling for billions of years does not reveal it. It is like trying to tell whether the earth is round while standing in a meadow. You do not see the curve, but it is there all the same. Cosmic geometry also affects the fate of the universe. In a closed universe, gravity might eventually slow down the expansion and cause everything to contract, leading to a big crunch. In an open or flat universe, expansion could continue indefinitely, thinning out matter and cooling the cosmos into a gentle fade. Though with dark energy pushing things apart ever faster, the big crunch seems unlikely. At least with what we know today, what is particularly comforting, in a quiet kind of way, is that no matter the shape, we are part of it. Whether the universe loops or drifts, curves or stretches, we are woven into its structure. Our atoms obey its geometry. Our light traces its curves. Our thoughts echo through its halls. We do not just live in space. We are space, folded into itself in a dance of mass and motion. So if the universe is flat, we live in a grand plane of cosmic possibility. If it is curved like a sphere, we may be looping around inside an invisible bubble. If it is open, we are surfing an endless saddle, heading out into infinity with no round trip planned. Whichever version is true, it is strange, elegant, and beautifully confusing in just the right measure. And that is part of the magic. You do not need to pin down the shape of space to appreciate its mystery. You can simply gaze up, smile at the stars, and know that you are standing on a tiny patch of something grand and curious. A universe with a shape we are still trying to imagine from the inside out. Imagine you are a tiny creature living on the surface of a balloon. You can walk north, south, east, and west along the surface, but you cannot dig down or float above it. Your entire world is that two-dimensional skin, curved but seamless. You do not know the balloon is being held by a giant cosmic toddler with a helium tank. You just know that when you walk straight, you eventually loop back to where you started. This is the magic of curved space. It plays by rules that do not always match our everyday experience, and yet it makes perfect sense once you slip into its rhythm. And while we humans live in 3 dimensions of space, curved surfaces in 2 dimensions give us a surprisingly useful way to imagine what our universe might be doing on a much grander scale. Let us start with something simple. On a flat surface like a sheet of paper or a calm tabletop, geometry behaves in familiar ways. You can draw a triangle and the angles will always add up to 180 degrees. If you draw 2 parallel lines, they will never meet. And if you start walking in a straight line, you will keep going forever unless you hit a wall or an unfortunate coffee spill. But now imagine walking on the surface of a sphere. Say a planet or that balloon we mentioned earlier. Geometry starts acting a little strange. If you draw a triangle using great circles like the equator and lines of longitude, the angles can add up to more than 180 degrees. Parallel lines, they do not stay parallel for long. They converge at the poles or drift apart depending on the path. Most importantly, if you walk in a straight line on this curved surface, you will eventually come back to where you started without ever turning around. No edges, no borders, just a continuous loop. From your limited perspective on the surface, the space around you feels infinite, but in reality, it is finite and curved back on itself. Now take that concept and scale it up. Imagine our entire universe as a 3-dimensional version of that balloon surface. Except instead of curving in 2 dimensions, it is curving in 3. Or rather, in a way we cannot easily visualize, because it curves in higher dimensional space. You and I live inside this 3-dimensional space, moving through it without ever seeing the outside. Just like the balloon creature never sees the air around the balloon. In this analogy, the galaxies are like dots drawn on the surface of the balloon. As the balloon inflates, the dots move farther apart, not because they are crawling across the surface, but because the surface itself is stretching. This is what cosmologists mean when they say the universe is expanding. It is not that galaxies are flying through space like comets on holiday. It is that space itself is growing, carrying galaxies with it. And just like our little balloon creature, if the universe is truly curved and finite, then traveling in a straight line long enough might eventually bring you right back to where you began. You would not fall off the edge of space because there is no edge. The loop closes smoothly. It is a finite space with no boundary, which is a strange and lovely idea. You could go on an infinite journey through a finite universe, never hitting a wall, never running out of room. The balloon analogy also helps us understand something else: why there is no special center of the universe. Just as there is no single center on the surface of a balloon, the universe does not have a central point from which everything is expanding. The expansion happens everywhere at once. Every point on the balloon moves away from every other point as it inflates. You could pick any spot and call it here, and the view would look the same in all directions. It is worth pausing here to note that the balloon analogy is not perfect. It is just a model to help our three-dimensional brains wrap around a higher dimensional idea. The balloon's surface is two-dimensional and embedded in three-dimensional space, which we can see and picture. But if our universe is curved, it might be curved in a higher dimensional space we cannot observe directly. It is not floating in a larger container. Space does not need an outside to curve. It can curve intrinsically by its own properties without reference to anything external. This idea of intrinsic curvature is one of the great insights of Einstein's theory of general relativity. Space and space-time more broadly is not a passive backdrop. It has shape and structure, and that shape can evolve over time. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. It is a beautifully circular relationship, one that governs everything from the orbits of planets to the behavior of galaxies on the larger scales. The curvature of space also affects the path of light. In curved space, light does not travel in straight lines as we understand them. It follows the shortest path available, called a Zzzcience, on a sphere that is a great circle. In our universe, it is a curved trajectory that bends under the influence of gravity and the shape of space itself. That is why massive objects like stars and black holes can bend light, a phenomenon known as gravitational lensing. So when we gaze out at the night sky, we are not just seeing objects scattered through flat, empty space. We are seeing a web of light moving through curved space, stretched and bent and shaped by the mass of everything around it. It is like looking at the stars through a slow-moving funhouse mirror, except the distortions tell us something true about the shape of the cosmos. Now, let us return to our balloon one last time. As it inflates, the distances between the galaxies on its surface grow. But the galaxies themselves do not expand. They stay the same size. That is because the expansion of space happens on large scales between objects not gravitationally bound together. So our Milky Way, our solar system, even our planet and its crusty old coffee shops, none of those are getting stretched like taffy. The expansion only takes hold in the great emptiness between galaxies. And what is driving this expansion? Well, we now believe that dark energy, a mysterious form of energy inherent to space itself, is causing the universe to accelerate in its growth. It is like the balloon is not just inflating, but doing so faster and faster with every breath. We do not know exactly what dark energy is, but we can see its effects in the way distant galaxies move and how ancient light spreads across the sky. So where does this leave us? It means we live in a space that might be curved, that might be finite yet boundless, expanding yet pitiless, shaped by rules that defy our everyday experience yet make perfect sense in the grand cosmic dance. And all of this, the curves, the expansion, the possibility of looping back to our starting point, can be imagined with a simple balloon, a rubbery metaphor floating through thought space, whispering ancient secrets about a universe that grows not outward from something, but within itself. Next time you see a balloon rising into the sky, give it a little nod. It may be full of helium and squeaky good fun, but it also carries within it the shape of something much greater, a gentle curve, a stretch of space, and the quiet idea that maybe, just maybe, the place you are headed is also the place you started. Only now you have traveled the universe to get there. One of the strangest ideas in modern physics is that our universe might not be the only one. Imagine for a moment that everything you know, every star, every galaxy, every law of physics itself, is just one bubble in a vast cosmic foam. Beyond our bubble, there could be countless others, each with its own properties, its own histories, maybe even its own versions of reality. This concept is known as the multiverse, and while it sounds like science fiction, it actually arises quite naturally from several scientific theories. Let us start with inflation. Earlier, we talked about cosmic inflation, the period right after the Big Bang when space expanded faster than the speed of light. According to some versions of this theory, inflation may not have ended everywhere at once. Instead, it might have ended in some regions while continuing in others. This creates bubble universes, pockets where inflation stops and a universe like ours forms, surrounded by a still inflating background. Each bubble could be infinite on its own, yet just one of many in the ever-growing froth of the multiverse. What makes it even more fascinating is that these universes might not all follow the same rules. In one bubble, the laws of physics could be slightly different. Maybe electrons are heavier. Maybe gravity is weaker. Maybe stars never form. Or maybe they burn in colors we cannot imagine. In another bubble, there might be no atoms at all, just exotic particles drifting in a bizarre space that would look utterly alien to us. Another path to the multiverse comes from string theory. String theory suggests that the fundamental building blocks of reality are not particles, but tiny vibrating strings. Depending on how these strings vibrate and how extra dimensions are shaped, you can end up with many possible versions of physics. The number of possible configurations is staggering, like 10 to the power of 500. That is a 1 followed by 500 zeros, an unimaginably huge landscape of potential universes. Some scientists believe that our universe is just one point in that landscape, one version where the strings happen to settle into just the right pattern to allow stars, planets, and life. And then there is the many worlds interpretation of quantum mechanics. This idea suggests that every time a quantum event happens, every time a particle has multiple possible outcomes, all of them actually occur. The universe splits, branching into parallel realities. In one, the electron spins up. In another, it spins down. In one, you chose tea. In another, you chose coffee. In one, you pressed play on this video. In another, you fell asleep before it started. In this picture, the multiverse is not a collection of separate bubbles in space, but a vast branching tree of possibilities, all equally real, all equally endless. Now, before we get carried away, it is important to say that the multiverse is still highly speculative. We do not have direct evidence of other universes. These ideas arise from theories that are otherwise quite successful at explaining what we see. But when extended, they suggest the possibility of many worlds beyond our own. For now, it is more philosophy than observation. But that does not make it any less enchanting to imagine. Because if the multiverse is real, it changes everything about how we see ourselves. We would no longer be living in the only universe, but in one of perhaps infinitely many. Our cosmos would not be the whole story, but a single page in an infinite library. Somewhere out there might be universes almost identical to ours, where history unfolded the same until one tiny detail shifted. And somewhere else might be universes so radically different that we would not even recognize them as universes at all. There is also a quiet comfort hidden in the idea of the multiverse. If there are infinite universes, then every possibility is realized somewhere. Every dream you have ever had, every path not taken, every version of yourself you sometimes imagine could exist in another reality. Not in the way comic books portray with dramatic crossovers and superhero team-ups, but in the quiet mathematical sense that somewhere in the endless sea of possibilities, another you is living a slightly different life. And even if we never detect these other universes, the very idea stretches our minds. It reminds us that what we call reality may be just one arrangement among countless others. That the rules we take for granted might be local, not universal. That the cosmos itself might be far stranger than our imaginations can grasp. So the next time you stare at the night sky and feel small, remember this: you are not just looking at one universe. You might be looking out from a bubble floating in an infinite sea, a bubble that just happens to support stars, planets, and the quiet miracle of life. And whether or not the multiverse is ever proven, it teaches us something valuable. That reality is richer than it first appears. That possibility is always larger than certainty. And that even within our one observable universe, the mystery is already more than enough to fill a lifetime of wonder. If the universe is expanding, if galaxies are racing away from one another, if space itself is stretching faster and faster, it is natural to wonder, will it ever stop? Will it turn around? Or will it keep going forever until everything drifts apart into a cold and silent emptiness? These questions bring us to the ultimate fate of the universe, a topic that is both sobering and strangely soothing. Scientists have proposed several scenarios for how the universe might end, each one shaped by the balance between matter, gravity, and dark energy. Let us take a slow walk through them. The first possibility is the Big Crunch. In this model, gravity eventually wins. The expansion slows, halts, and then reverses. Galaxies begin moving closer together. Stars and planets collide. Temperatures rise. In the end, the universe collapses back into a dense, hot state, perhaps not unlike the conditions of the Big Bang. Some theories even suggest that a new Big Bang could follow, leading to a cycle of births and deaths, an eternal cosmic heartbeat. Though current evidence, with dark energy pushing the expansion faster, makes this outcome less likely, it is still a hauntingly elegant picture. A universe that ends not in silence, but in fire and renewal. The second scenario is the Big Freeze, sometimes called the heat death of the universe. This one is currently considered the most probable. Here, dark energy continues to drive expansion forever. Galaxies drift so far apart that eventually no new light reaches us. Stars burn out, one by one. White dwarfs, neutron stars, and black holes are all that remain. Over trillions of years, even those fade, evaporating slowly through processes like Hawking radiation. The universe becomes a cold, thin, dark place, with temperatures approaching absolute zero. a cosmic winter without end. It sounds bleak, but there is a kind of peace in it too. A slow fading rather than a violent collapse. The universe simply exhales until nothing is left to say. Then there is the big rip. In this dramatic ending, dark energy does not remain steady. Instead, it grows stronger over time, pulling space apart at an ever-increasing rate. Galaxies not only move away from each other, but are eventually ripped apart themselves. Stars, planets, even atoms are torn asunder as the very fabric of space accelerates beyond all limits. It is the most violent of the endings, a shredding of reality itself. If dark energy behaves this way, the final moments of the universe would be catastrophic. But so far, the evidence suggests that dark energy is constant. So the big rip remains more of a dramatic possibility than a likely forecast. A quieter possibility is called the big slurp, tied to an idea in quantum physics. According to this scenario, the vacuum of space that we live in might not be truly stable. It could be a false vacuum, a temporary state that could one day decay into a lower energy vacuum. If that happened, a bubble of true vacuum would form somewhere and expand at nearly the speed of light, rewriting the laws of physics inside it. In an instant, everything we know, every star and atom, would be redefined. It is not the most comforting idea, but physicists assure us it is highly unlikely to happen anytime soon. Still, the name Big Slurp does sound almost cozy, like a cosmic hot chocolate gone wrong. Each of these endings highlights a truth about the universe. It is not static. It is not eternal in its current form. It is a story with a beginning, a middle, and an end. Whether that end comes in fire, in ice, in a rip, or in a slurp, the universe will not remain as it is forever. But here is the gentle part. These endings are not near. They lie trillions of years in the future, far beyond the lifespan of Earth, the Sun, or even the Milky Way. We have time to wonder, time to look at the stars and enjoy their glow, time to marvel at the strangeness of existence without rushing to its conclusion. And maybe, just maybe, the universe's ending is not an ending at all. Some theories suggest that the Big Crunch could lead to another Big Bang, that heat death might give rise to quantum fluctuations and a new universe bubbling into existence, that our cosmos could be one note in an endless symphony, each universe giving way to another. If that is true, then death is just another form of birth, and the story never truly stops. So when you think about the fate of the universe, do not let it fill you with dread. Let it calm you instead, because no matter how it ends, it will be a long, slow, graceful process, far beyond our little lifetimes. And knowing that, we can simply sit back beneath the stars and enjoy the show. A show that, like all good things, will one day reach its final act. But what an act it has been. When we talk about space, we often describe it as something out there, above our heads, beyond the clouds, past the atmosphere, a realm of stars and galaxies and black holes, separate from our daily lives. But in truth, space is not out there. It is here. It is everywhere. You are living in it right now, breathing in it, made of it. Because space is not just the absence of matter. It is the stage on which matter performs, the fabric that gives structure to everything. And it is not empty. It is humming, stretching, and bending all around you. Even here, in this quiet moment, sitting wherever you are embedded in space-time, woven into its texture like a thread in a vast cosmic quilt. This idea can feel abstract, but let us bring it closer to home. Take the simple act of sitting in a chair. Gravity is pulling you downward, holding you to Earth's surface. But according to Einstein, what you feel as gravity is really the curvature of space-time. Earth's mass bends the fabric, and you are simply following the natural path through that curve. Your chair pushes back not because gravity is pulling you down in a literal sense, but because space-time is guiding you that way, and the chair refuses to yield. Your body, too, is made of particles that arise from quantum fields filling all of space. Electrons, protons, photons, all dancing excitations of fields that exist everywhere. Even the emptiest corner of the universe is not truly empty. It is alive with these fields, with fluctuations, with vacuum energy, the same quantum activity that hums between distant galaxies is humming between the molecules of your skin right now. In fact, the atoms in your body were forged in stars, carried here by the expansion of space itself. Every breath you take contains molecules once exhaled by ancient forests, once touched by oceans that shimmered under younger suns, once part of stars that lived and died long before Earth even formed. You are not separate from space. You are its expression, a local arrangement of atoms, a temporary ripple in a sea that stretches forever. This connection extends farther than we usually allow ourselves to feel. When you look at the stars, you are not looking at something foreign. You are looking at family. You are made of the same elements, shaped by the same physics, governed by the same geometry. The light from distant galaxies, the curves of space-time, the hum of quantum fields. It is all part of the same continuous reality that includes you. And maybe that is the quiet gift of asking where space ends. The more we try to find an edge, the more we realize there is none. The universe is not a box we live inside. It is the fabric we are woven from. There are horizons, yes, limits to what we can observe. But those limits are not the edge of existence. They are just the edge of what we know. Beyond them, reality continues, curving and expanding, humming with possibilities. So, does space ever end? Probably not in the way we imagine. There may be no wall, no border, no finish line. Just more space, more time, more mystery. The universe may be infinite, or it may be finite but unbounded, looping gently back on itself. Either way, there is no edge to fall from, no outside to escape to. Just the quiet, endless presence of space-time itself. And within that endlessness, there is you. A tiny collection of stardust, conscious for a brief flicker, looking up and asking questions. Questions that may never have final answers, but that carry their own beauty in the asking. Because to wonder where space ends is to admit that you are part of something larger. Something without edges. Something that stretches beyond imagination. So tonight, as you close your eyes, let that thought cradle you. You are not alone in the dark. You are part of the dark. You are part of the light. You are part of the space that fills everything. And that space, mysterious and boundless, is also part of you. Asterisk, asterisk. There is a quiet poetry in the way science circles back to wonder. We start by asking simple questions. Where does space end? What is it made of? How far can we see? And in chasing those questions, we discover answers that are never final, always unfolding into deeper mysteries. Think of the cosmic microwave background. At first, it was just a faint hiss. A static picked up by a radio antenna in the 1960s. Nothing more than an annoyance for two engineers trying to calibrate their equipment. But that hiss turned out to be the afterglow of the Big Bang itself. a whisper from the universe when it was only 380,000 years old. A reminder that even the faintest noise can carry the oldest secrets, or consider the discovery of dark energy. Astronomers set out to measure how fast the universe's expansion was slowing down, expecting gravity to be pulling everything back. Instead, they found it was speeding up, as if the universe had decided to surprise them with a plot twist no one saw coming. A quiet acceleration, invisible yet unstoppable, woven into the very fabric of reality. Each time we think we are reaching the edge of knowledge, the horizon expands. Each answer becomes another question. And that cycle, that endless unfolding, is what makes science not just a tool, but a kind of meditation. A way of seeing the world not as something to conquer, but as something to sit with, to listen to marvel at. Because in the end, space is not just about distances and galaxies and cosmic microwave radiation. It is about perspective. Looking out at the stars reminds us that our worries, our deadlines, our tangled to-do lists, are tiny ripples on a very small pond. Out there, stars are being born, galaxies are colliding, black holes are humming softly at the centers of galaxies. The universe is alive with motion, and yet we are here, wrapped up in our own small stories. There is comfort in zooming out, in knowing that even the greatest human dramas are brief flashes against the backdrop of cosmic time. Wars begin and end, civilizations rise and fall, even entire species bloom and fade. But the stars keep shining, the galaxies keep drifting, space keeps stretching, and in that vastness, our troubles lose their sharp edges. They become lighter, easier to carry. So perhaps the answer to where space ends is less important than the journey of asking. Perhaps the point is not to find the boundary, but to remember that there may be none. That we live in a reality where limits dissolve into horizons, and horizons dissolve into mystery. As you let yourself drift into sleep, think of this. You are lying not just in a room, not just in a bed, but in a universe without edges, above. Galaxies spin quietly, stars flicker, and light travels patiently across billions of years. Below you, atoms hum with quantum energy, fields ripple, and space-time curves gently under your weight. You are cradled by the cosmos, held in its infinite arms. There may never be a final answer to the question of where space ends. But maybe that is the beauty of it. The mystery itself is the answer. A reminder that we do not need certainty to find peace. We just need wonder. When you listen closely to the story of the universe, you realize it is not just a story about stars and galaxies. It is also a story about us, about how matter, born in the hearts of dying stars, gathered into planets, into oceans, into living cells, into thoughts. You are not outside of the universe, looking in. You are the universe, looking at itself. Carl Sagan once said, "We are a way for the cosmos to know itself." And in a quiet way, that is true. The atoms that make up your body once belonged to ancient stars. The calcium in your bones was forged in supernova. The iron in your blood was born in the collapse of massive suns. Even the oxygen you breathe is a gift from stellar furnaces that lived and died billions of years ago. You are literally made of stardust, and that dust, for a brief and extraordinary moment, has come together into you, conscious, curious, capable of wondering where space ends. So when you ask about the edge of the universe, remember that you are not separate from the answer. You are part of the fabric itself, a ripple in space-time, pondering the sea it swims in. Your heartbeat, your breath, your thoughts, they are all echoes of cosmic processes. Small, yes, but no less real, no less beautiful. And here is the softest truth of all. Even if space has no edge, even if the universe is infinite, you still matter. Not because you are large or powerful, but because you are here. Because you are aware. Because in the vast silence of the cosmos, you are one of the few places where the universe speaks. So let the stars comfort you. Let the endlessness above you ease your mind. There is no rush to solve the mystery, no need to grasp the whole. It is enough to drift gently in the knowledge that you belong to something boundless. To close your eyes, to breathe, and to rest in the arms of space itself. Good night, traveler. May your dreams carry you far, and may you always remember that even in sleep, you are cradled by the universe.